So you're looking to really get a handle on something cutting edge, right? But without spending ages digging through dense reports.
Yeah, that's the goal.
Well, that's what we do here. Today, we're doing a deep dive into a really fascinating story in power generation. We've pulled together some great stuff to get you up to speed fast.
Absolutely. We're looking at Hyliion, specifically their big shift towards the Karno generator.
And the crucial role 3D printing additive manufacturing plays in all this.
It's absolutely pivotal, yeah.
And you've got some excellent sources for us. Comparisons between Desktop Metal Studio and Colibrium Additive's M series that gets into the nitty-gritty tech side.
Right, details.
And that fantastic Munroe live YouTube tour, Sandy Munroe getting a proper look inside Hyliion, seeing the Karno, really insightful.
Exactly. So our mission today, is to connect those dots. Why this specific 3D printing tech for the Karno, and what does it all mean for, well, the future of power?
Okay, let's jump right in. Hyliion. They were really focused on the electric truck market before, weren't they? The Hypertruck ERX.
They were heavily invested. But then, late 2023, they made a pretty big pivot.
A decisive move, he said?
Yeah, I think so. They basically exited the electric truck side completely. All focus now is on the Karno generator, aiming squarely at stationary power.
That's a bold strategy shift.
It really is. Signals a whole new direction.
And the Karno generator itself, it's got this really interesting core feature, hasn't it? It's fuel agnostic.
That's the key. It's the design. This linear architecture lets it use a whole range of fuels. We're talking natural gas, hydrogen, propane, ammonia,
Wow.
even potentially waste heat. That kind of flexibility, that's a huge plus in today's energy landscape.
So it's not tied to just one fuel source. And the Munroe video, I remember them saying it's modular, too.
Exactly. Scalable. Tom Healy, the founder, mentioned potential uses like data centers, big commercial buildings, EV charging sites.
Even marine applications, I think.
Yeah, marine vessels, too. So think distributed power, tailored where you need it.
Okay, now here's where it gets really interesting, I think. The sources make it super clear that additive manufacturing, this advanced 3D printing, it's not just helpful for the Karno, it's essential. Why is that?
Well, that comparison document between Desktop Metal and Colibrium really highlights it. The Karno needs parts with incredible complexity and precision to work efficiently.
Things like heat exchangers, thermodynamic systems.
Exactly. Geometries you just couldn't make, or certainly not cost-effectively, with traditional machining or casting. LPBF's precision, even if it takes longer per part sometimes, lets them engineer much more efficient components.
Right. That makes sense. The old ways just can't cut it for this level of detail.
And it's not just about complex shapes. There are other benefits.
Like what?
Well, huge design freedom, obviously. Optimizing parts in ways you couldn't imagine before. Less material waste is a big one, too.
Oh, yeah. The Munroe video mentioned that 99% recyclability for the metal powder. That's impressive.
It really is. Good for the environment, good for the bottom line. Yeah. Plus, you get these really robust, high-performance parts built specifically for the job.
I remember that cutaway view in the Munroe video. Josh, the VP of engineering, pointing out the super tiny fins inside the recuperator.
Yes.
He said you could only get those geometries with advanced additive. That was a real aha moment.
That's a perfect example.
Yeah.
Shows the power of laser powder bed fusion, LPBF. Maximizing efficiency in ways traditional methods just can't touch.
Okay, so let's get into the specific tech. Hyliion is banking on Colibrium Additive's M-line system now for scaling up Karno production. Is that right?
That's what the sources indicate, yes. They've installed the first M-line in the U.S., apparently, with more machines ordered through 2025.
Sounds like a serious commitment.
It does. And they're expecting a big jump in production capacity.
How big?
Something like 2 to 4 times their previous 3D printing output. That's what they're aiming for. Essential if they want to meet demand for Karno.
And the M-line uses this LPBF, laser powder bed fusion. Can you break down what that actually involves?
Sure. So imagine a bed of very fine metal powder. A powerful laser beam then melts and fuses the powder, layer by tiny layer, following a digital design.
Layer by layer.
Exactly. The build platform lowers a fraction, a new thin layer of powder is spread, and the laser goes again, building it up from scratch.
And the M-line system itself, I heard its modular design is a big plus.
Yeah, that's quite clever. It separates the laser part of the actual melting from the powder handling, the logistics of the material.
Okay, so that streamlines things, reduces downtime.
Pretty much. Different stages can work more independently, makes the whole production flow smoother.
And it's worth remembering, Hyliion isn't totally new to this, right? They used GE additive machines before.
That's right, an X-Line 2000R, also LPBF, for aluminum parts, so they have experience.
Yeah.
This focus on the Colibrium M-line probably just means it fits their current scale-up strategy for the Karno components best.
Which brings us neatly to desktop metal, another big name in metal 3D printing. But Hyliion seems to be leaning towards Colibrium. Why might that be? What's the difference in their tech?
Good question. Desktop metal has technologies like bound metal deposition, BMD, and binder jetting. They work differently.
How so?
Well, BMD uses a filament, metal powder, mixed in a polymer binder. You print it, then you have 2 steps. Debinding to remove the polymer, then sintering in a furnace to fuse the metal.
Okay, so extra steps. What about binder jetting?
Binder jetting uses a liquid binder, like an inkjet printer, to stick layers of powder together. But those parts also need that separate sintering step afterwards to get strong and dense.
Right, so LPZF, the M-line tech, it sounds more direct, just melting the powder with the laser.
Generally, yes. LQBS usually gets you very high density, almost the final shape right out of the printer. You might still need some finishing, but the core process is direct melting. BMD and binder jetting are more indirect because of those debind and sinter stages.
And what about those super complex parts that Karno needs? How do they compare there?
Well, the sources suggest LPBF really shines for those intricate internal structures. Just what the Karno seems to need for efficiency.
So maybe higher precision with LPBF.
Often, yes, especially for very fine critical features. Binder jetting and BMD can do complex shapes too, but LPBF often has an edge for that ultimate intricacy.
And scalability. Hyliion needs to make a lot of these Karnos eventually.
That's key. Colibrium's M-line is definitely built for series production, scaling up industrially. Desktop Metal's production system, using binder jetting, is also geared for high volume. But Hyliion choosing the M-line right now suggests that for the Karno-specific needs, the performance, the density, maybe the exact type of complexity, LPBF is their preferred route to get the volumes they need now.
So it really boils down to the specific engineering challenge of the Karno. The complexity, the material properties, the production goals. LPBF just seems to tick the right boxes for them at this stage.
Exactly. It's not about one tech being better overall. It's about the best fit for the job. And for the Karno, LPBF's precision and material qualities seem absolutely critical.
Let's dig just a bit more into that LPBF versus binder jetting comparison for industrial use. You said they each have sweet spots.
They really do. Understanding where each excels is interesting. LPBF, like the M-line, tends to be favored when you need absolutely top-tier material performance and really complex shapes, even if you're not making millions of them. Think aerospace parts, custom medical implants.
High value, high complexity.
Right. Binder jetting, on the other hand, can be really strong for higher volumes of complex parts, where cost per part becomes more critical. You see it more in automotive, maybe consumer goods.
So LPBF for the really demanding stuff. Binder jetting potentially for bigger batches where cost is key.
That's a good way to put it. Hyliion going with LPBF strongly implies the Karno parts have some really tough performance specs that need that direct laser melting approach.
Okay, shifting gears a bit. That Munroe live video, it was such a great look inside Hyliion. Tom Healy and Josh, they were really open about their fail-fast approach, weren't they?
Yeah, that really came across. They weren't afraid to show the learning process, the prototypes that didn't quite make it.
Seeing the evolution from the early, more segmented Karno designs to the final, more integrated one really showed that refinement process.
Definitely illustrated how they iterated towards the final design.
And they broke down the Karno's main parts so clearly. The linear motor in the middle.
Right, generating the electricity.
And the cold side, compressing the helium. The heater, expanding the helium.
Creating the pressure.
And the reactor itself, turning fuel into heat.
Understanding those 4 bits is key to getting how it works. It's this closed-loop system. Heat the gas, it expands, pushes the motor, cool the gas, compress it, repeat. Pretty elegant.
And those efficiency numbers they mentioned were pretty impressive. 60% system efficiency, 50% net. Double what you get from typical combustion engines.
That's a huge jump. Capturing and reusing heat so effectively makes a massive difference in reducing wasted energy.
The video also showed their actual additive manufacturing setup. The powder beds, the lasers working away, multiple lasers at once to speed things up.
Yeah, seeing those machines literally growing complex metal parts from powder really drives home how transformative this tech is.
And the fact that one part, like that cold side component, could take days, maybe a week to print. thousands of layers.
It really highlights the complexity involved, doesn't it? It's not a quick process for these intricate parts, but it enables things that were impossible before.
And that powder removal system, the silicon, getting back 99% of the material, that's just fantastic for sustainability and cost.
Absolutely. Minimizing waste, maximizing resource use, it's a core advantage of additive.
Josh's comment about creating previously impossible geometries, the egg in a ball analogy that stuck with me.
That really captures the design freedom, doesn't it? Those internal structures, optimized for heat transfer or fluid flow, give the Karno its edge.
They also showed a smaller 3D printer they use for R&D, testing materials and early concepts. It seems smart.
Definitely. Test things out quickly on a smaller scale before you commit to the big production machines. Speeds up innovation, reduces risk.
Then we saw the whole package 200 kilowatt Arno unit, all the supporting gear, fans, radiators, pumps, the balance of plant, they called it.
Right. Everything needed to make it work in the real world.
And that small lithium titanate battery. Not for long duration, but for handling quick power surges.
Exactly. It smooths out the demand, complementing the Karno's steady output. A nice bit of system integration.
Tom and Josh walk through the inside again. Central motor, cold side, hot side reactor around it. It looks really compact for what it does.
It is. And the sealed core system trapped helium, those gas or air bearings, instead of traditional ones that suggests potentially much lower maintenance needs.
Yeah, no oil changes.
Right.
And that demo with the coin, balancing perfectly on the 4-shaft production unit while the older single-shaft prototype vibrated.
That was brilliant. Really showed the engineering they put into making the production unit smooth and stable. Very effective visual.
Another thing that struck me was how little post-processing they said is needed because the printing is so precise.
Yes, that near-net shape capability of LPBF means less machining afterwards. They only need to finish critical surfaces, like seals.
Saves time, saves cost.
Absolutely.
What about startup? Around 30 seconds to get some power, maybe 4 minutes to full power. It's not instant, but still pretty quick for a thermal system.
It is. And that fuel sensing capability they mentioned, automatically detecting and adjusting to different fuels, that's clever for a fuel-agnostic design.
And the thermal storage for brief fuel hiccups adds reliability, too.
Right. Covers those little interruptions.
They prefer gaseous fuels, but can use others without worrying about things like engine timing or compression ratios. That flexibility seems fundamental.
It really is. By separating the heat generation from the electricity generation, they bypass a lot of the limitations of internal combustion.
And the emissions performance, beating California standards without needing complex exhaust after treatment. That's huge.
Definitely a major environmental plus.
Yeah.
Getting those low emissions just through the basic design, the continuous reaction, the heat recuperation. It's impressive engineering.
Even handling leftover solids from heavier fuels with filters shows they've thought through the practicalities of using diverse fuels.
Yeah, it shows they're thinking about real-world operation, not just the ideal scenario.
And lastly, the fact that Karno outputs DC power natively with AC inversion as an option. That fits with the push towards DC systems that Sandy Munroe often talks about.
It does. Direct DC can be more efficient, avoiding conversion losses, especially for things like EV charging or modern buildings.
Tom Healy's final thought in the video really summed it up, didn't it? That additive manufacturing is finally unlocking the potential of a 200-year-old power concept.
It's a powerful point. Shows how new manufacturing tech can breathe life into established science. Feels like a real step change.
So, wrapping up our deep dive, it seems crystal clear. Hyliion's bet on Colibrium Additive's M-line, that LPBF technology, it's not just part of the Karno story, it's absolutely central to making it happen.
Totally. It's the enabler. Without that ability to make these incredibly complex, high-performance parts efficiently, the Karno concept probably stays on the drawing board. LPBF lets them build it and scale it.
And hopefully, for everyone listening, this dive gave you some of those aha moments, seeing how the Karno's clever design and this advanced manufacturing are completely intertwined.
Yeah, understanding that connection really shows how innovation in one area, like manufacturing, can unlock breakthroughs somewhere else entirely, like energy.
Okay, so here's a final thought to chew on after we finish. We've seen how advanced manufacturing is enabling distributed fuel-agnostic power like the Karno. How could this start to reshape our whole energy system in the coming years?
Big question.
Yeah. Beyond data centers and EV chargers, what new possibilities open up for industries, for communities wanting more resilience, maybe even for individual homes looking for more energy independence? It's definitely something to think about as this tech keeps evolving.